A small plane is 100 kilometers due east of Denver. So let's say this is Denver. And let's say this is 100 kilometers east, right? This is east. And after 1 hour of flying at a constant speed in the same direction, it is 200 kilometers due north of Denver. So from here, it reached that spot and it flew for 1 hour. And this is 200 kilometers. Okay, so the question is, what is the plane's velocity? And they said it's moving with a constant velocity. What is the direction of the velocity? A to B, right? That is the direction. Now that's the direction of its displacement. In this case, it's also the direction of its velocity. Since this is a fixed velocity, the velocity is the same throughout, right? Otherwise, it could have been changing its magnitude and direction on the way. So that means the velocity vector is also pointing this way. Now we have to define, right? Assuming x is along E and y is along N, we have to find what this V is. So this vector is called the displacement. The reason it is not, we don't normally use D is because we often work with calculus and D, you know, is used for the differential, right? D over dt. So there are already many D's. We don't want to introduce one more D. So we usually you see S. So displacement S, the magnitude of the displacement is. So that is the distance that it traveled in the straight line. And it traveled that in 1 hour. So the magnitude of velocity, which is speed, kilometers per hour. Now we still need the direction. So if we draw that again, and if I take this as theta, and this is 200 and that's 100, right? Then theta is tan inverse 2, which is 63.4 degrees. So how do we say this? This is west of Denver, right? And we are going which way? We say due 63.4 degrees north of west. Starting from west, moving north, and we move by 63.4 degrees, then that's the direction. Velocity is 224 kilometers per hour, 63.4 degrees due north of west. We've already used this idea, but let us define velocity and acceleration in these scenarios. Average velocity, displacement over elapsed time, right? So that doesn't change. That is still what was there before, correct? But now displacement is a vector, right? So this displacement you would find as the S vector, final position minus initial position over delta t. And if this is the displacement vector S, then what is S equal to? R2 minus R1. Usually these things work out as final minus initial, right? If R2 is your final position, then the displacement is R2 minus R1. So R final minus R initial over delta t. Okay, and similarly, average acceleration will be delta V over delta T, right? Velocity final minus velocity initial over delta T. In case of instantaneous, since you know the calculus, you just pay attention that we're working with vectors. The R is the vector and the V is the vector. Time is not a vector. The velocity can change even if just the direction changes. You could be going with the same speed, but if you change direction, your velocity has changed. And that's what we will see in uniform circular motion.